Good Saturday morning. My name is Casey and you are watching Programming is Easy. A lot of people without a formal computer science degree always get tripped up by different data structure. When I myself first encountered the implementation of linked lists, queue, stacks, or even an array, I always feel like I'm in a haunted house in which I can never get out of it because I can never understand what they are doing. Today, we are going to take you through the Halloween favorite of all. A tree data structure. In particular, a binary search tree. Many of us find tree and graph data structures tends to be the most difficult concept. Searching through a tree is more complicated than searching in a linear data structure, such as an array or linked list. On top of that, the worst case and average case time and space complexity for trees can vary widely, which adds another layer of complexity to the already complex problem. Therefore, being able to implement a tree from scratch is vital in order to get a deeper understanding of computer science and over time to do well in a coding interview. Before we dive into implementing a binary search tree, let's go through all these buzzwords. So the first one is tree, next one is binary trees, the next one is binary search trees, and another one is balanced versus unbalanced, and the last one is full, complete, and perfect binary search trees. So if you don't know any of these terms, don't sweat about it. I promise, after the video, you are going to be the expert of all these terms. A good way to understand a tree is with a recursive explanation, in which a tree is a data structure composed of nodes. Before we dive in to understand what is a tree, let's try to understand what is a node. Every single tree has a root node, and every root node has 0 or more child nodes. Within every child node, again, they should have 0 or more child nodes, and this could go on and on and on. And the node may or may not be in particular order, and they could have any data type as their values. A node with no children is often called a leaf node. A simple JavaScript implementation of a node could be as follows. Here, we are creating a constructor function of a node. That's why the n is capital N here. I'm passing on whatever the value of the node is, and we initialize the node, the this.value, value, as the whatever parameters that we pass in here. Here, we also initialize the this.left to be null and also this.right to be null. Remember, what we just talked about are trees in general. Remember, not all trees are binary trees. So let's differentiate what is the difference between a tree and a binary tree. A binary tree is a tree in which it could have up to 2 children per node. Remember, not all trees are binary tree. So let me show you an example here. As you can see here, this tree is not a binary tree because the root node has more than 2 children. For trees like this, we can actually call it a tertiary tree. Just remember, to be a binary tree, every single node could only have a maximum of 2 children. So if we take out 9 here, this will be a binary tree. So now that we understand the difference between a tree and a binary tree, let's also try to understand the difference between a binary tree and a binary search tree. A binary search tree is a binary tree in which every node must be greater than the left descendant and also smaller than all right descendants. Let me draw you a tree to show you what I mean. So as you can see here, the tree on the left is not a binary search tree. The reason being is because this descendant is not smaller than the root. So remember one thing, the left descendants applies to all the children, not just the immediate children. So that's why this is not considered a binary search tree. And as you can see here on the right side, this is a true binary search tree because every single node, including the children and not just only the immediate children, are smaller than the root node here. So you can see the left side are all smaller than 9. And on the right side, they are all greater than 9. So now that we understand what is a binary search tree and what is not a binary search tree, Let's go over what is a balanced tree and unbalanced tree. Well, many trees are balanced. Not all trees are. Note that a balanced tree doesn't mean the left side and the right side of the trees are identical. Think about it this way. A balanced tree actually means something like the tree is not terribly imbalanced. Just so that we can still do insert and find in old log n time. Now that we have go over the first 4 buzzwords, let's go over the last item on the list. Full, complete, and perfect BST. A complete binary search tree is a tree in which every single level is fully filled, except for the last level. A full binary search tree is a tree in which every single node can only have either 0 or 2 children. And a perfect binary search tree is the combination of a full and complete tree. But let me now draw you a picture of all these trees so that we can get better understanding of how they look like. As you can see here, a full binary search tree is a tree in which every single node has either 0 children or 2 children. 5 has 2 children, 12 has 2 children, 1, 8, 19 has 0 children. So, if any one of them has only 1 children, it would not be a full binary search tree. A complete binary search tree is a tree in which every single level is fully filled, except for the last level. As you can see, level 1 is filled, level 2 is filled, and this level is not fully filled, but this is the last level, so it's okay. And on the last level, it has to fill from left to right. So if there's a node here, and there's no node here, this would not be a complete binary search tree. The last example is the perfect binary search tree, in which is a combination of full and complete, meaning every single node has 2 children. As you can see, 10, 5, 15 has 2 children, 1, 7, 12, 20 has 0 children. And also, it has the characteristic of a complete binary search tree, in which every single level of the tree is fully filled. Now that we have a good understanding of what a binary search tree is, let's try to create an insert method to a new tree. Before that, let's put a constructor function for node. With the node constructor function, let's also create a new constructor function for the binary search tree. Inside this constructor function, we just simply initialize the root of the tree to be null. And then now we can create the insert method on the prototype train of the binary search tree. First, let's initialize a constant called root, where it will be the root of the binary search tree. We will then check to see if there are any root in the current binary search tree. Remember this AND operator, it will return true if there's currently no root, meaning the root is equal to null. If there's no root, we will then simply insert the new node as the root of the tree. After that, we can just return, since we already insert the new node to the tree. However, if there's currently a root, we will then set the current node equals to the root of the tree. Here, we cannot use constant because we will be reassigning the current node in our while loop that we are going to create below. And then now we will also create a new constant called new node, which would equal to the node that we would like to insert to the tree. And now let's create a while loop. We will keep tracking inside the while loop as long as the current node is truthy. And inside the while loop, if the value that we are about to insert to the tree is smaller than the current node value, we will then check to see if there is anything on the left side of the current node. Again, we're using the band operator here. And if there's nothing on the left side of the current node, we will then simply set the current node dot left to be the new node. We then break out of the while loop since we already insert the new node. However, if there is something on the left side of the current node, we then set the current node to be the current node dot left and continue the while loop. On the opposite side, if the value that we are about to insert is greater than or equal to the current node dot value, we will then check to see if there are anything on the right side of the current node. Pretty much the right side is identical to what we just did on the left side, but instead we'll be checking on the right rather than the left. So we just successfully create an insert method on the binary search tree. Let's test this out to see if it works. Let's create a new constant called BST, and we will call the constructor function. Then we will just insert 3 as the root of the node. And then we can insert another node called 2, maybe another 1 on the right side. And just for the fun of it, let's also insert 1 and 5. Now, let's console log the tree. Let's do a JSON stringify just so we can see all the details of the tree. And now, let's run on the repo. Oh, sorry, there's a typo. Let's try again. As you can see in the repo here, the root is 3, which is good because 3 is the first node that we insert into the tree. And then 2 is on the left side of the tree, so as 1. And 4 and 5 are both on the right side of the tree. So as you can see here, we have just successfully created a binary search tree. I hope you enjoyed this video. There are a lot of terminologies that we have gone through, such as a tree, a binary search tree, etc. I hope what my tutorial did is to help you demystify that binary search tree is in fact not that difficult. Once you take the time to understand how it works and what they are, we could learn better data structure and be good in the coding interview. Thank you.